Hey class, Adam Ward here. Welcome back, and what I'd like to talk to you about in this module is stream solute tracers, sort of what and why. So you are embarking on a road to understand stream solute tracers. Let's get ourselves on the same page about what these are, some of the major uses that we have, and how this is all going to work. Okay, so stream solute tracer study in three primary steps. Step one, we take a known mass of some chemical, which we'll call our tracer, and we release it at some location. You can see in some of the images below, these are fluorescent dyes, bright red or bright green. In the upper right image, the release is sodium chloride or sodium bromide, so a colorless, odorless salt. You can see some folks who are dumping over buckets, and you can see the upper middle picture. They've actually got a big tank sitting on the banks of the stream, and they're slowly pumping that dye in at a constant rate. But all of those have the same thing in common. We release some tracer at a given location. Step two, at some downstream location, we record a concentration time series. So we look for that tracer back. We release it at point 1, we look for it at point 2. And ultimately what we're able to do is interpret that concentration time series to learn about transport through our study reach and possibly transformation if we've released a chemical that is reactive, or if we've released multiple chemicals, one of which reacts and one doesn't. Nitrate and bromide as an example. Okay, now I won't show you the video here, but in this module you can see a recording of a tracer study in a large river being launched by a group of students that I worked with out at the University of Iowa. So what's going to happen to that tracer after we release it in the stream? So here's a schematic of a stream flowing from left to right with our tracer release or our input shown in red and the place we would measure the concentration time series shown in orange. And so if we put in a pulse of tracer, sort of this instantaneous release, if the only thing that happens out there is advection, what we would expect is downstream to see that exact same shape come by a bit of time later. So for our purposes, advection is sort of like putting our tracer on a conveyor belt, right? It's going to move from one place to another, but the shape shouldn't change. It should just be shifted in time. Now that's not what typically happens. We tend to get mixing with other water, and that's driven by random motions and concentration gradients in a process we call dispersion. And so if we have both advection and dispersion, what we would get back is a time series that looks like this pink time series. So typically sort of a normal distribution. If there was a lot of dispersion in our study reach, we might get back something that looks like this green breakthrough curve or this green concentration time series. And so perhaps what you can see already is that how long it takes something to move through our study system will teach us about advection, and how spread out or not spread out that shape is will teach us something about dispersion in the system. So again, advection, like a conveyor belt, this is shifting our time series but not changing its shape. And dispersion is giving us that symmetrical spreading around the advective timescale. Well, those aren't the only processes that are going to happen along the way. One of the really popular things that you can learn from solute tracer studies is about temporary storage or transient storage. And so the two images here are to sort of give you the sense that although much of your tracer will be advected and dispersed through the study reach, there are other places that your tracer might go. And so in the schematics on the left-hand side, what we're illustrating here is in-stream storage. So think like a recirculating eddy, a whirlpool, a still-looking pool behind a log where most of the water seems to be going around it. What happens in these temporary storage zones is that water and solute get into them. They spin around in these whirlpools or eddies. They spend more time there than you would expect just from advection and dispersion alone, and then they come back. So the image on the right is a time lapse. What look like white streaks, these are sort of bubbles, and if we leave the lens open for several seconds, we can see the circulation actually beginning to happen there. Now, in addition to this happening in the surface, that kind of storage also happens in the subsurface. Throughout these lectures, I'll use the words hypereic exchange to denote any time water goes from the surface stream or river into the subsurface and back again. Now, that could be through a bed form, that could be cutting through a meander bend, that could be laterally around a pool riffle sequence, or really any of these features where you have water leaving the stream and coming back. And the reason we care is that this slows down water and tracer. So while we would expect advection and dispersion to be dominant, if we get lots of temporary storage, lots of hypereic exchange, what we start to do is deviate from that advection dispersion profile. Now, we've already seen this idea that if we put tracer into a stream and the only thing that happens is advection, that just gets translated. If we have advection plus dispersion, as shown in orange, we get these sort of symmetrical concentration time series. And if we have advection, dispersion, and transient storage, either in the surface and or hypereic zone, what we get back are time series that have this late time tailing. They look like they are leaning to the left with a long tail on the right-hand side, or at late time. And so from the shape of these breakthrough curves, we can start to understand what kind of transport has happened along the way. Has it been advection? Has it been mostly advection dispersion? Do we get lots of late time tailing that would indicate transient storage? So we will spend a lot of time this module unpacking the shapes of these breakthrough curves and how we can infer processes from those shapes. The last slide I want to leave you with is, what the heck good is a solute tracer study? Why would you do this in the first place? Well, solute tracer studies can be used to inform our understanding of transport conditions or mechanisms, A, D, and TS, meaning advection, dispersion, and transient storage. And I'm going to also add here and discharge. Or am I? Let's do and Q, meaning volumetric discharge. So a really popular reason to do a solute tracer study is to estimate the discharge in a study reach that's otherwise ungauged. With knowledge about transport and flow, this is a basis to forecast what would happen if there was a spill, what will happen if my client starts to release wastewater as they propose. If we understand physical transport, so just the how water and what's in it moves, that's a prerequisite for reactive transport. So we first must understand transport before we can add transformation or reactivity to it. And with this knowledge, we're able to answer important questions like, if there's a spill, how long until the pollutant is gone? Or how bad is it going to get? Which typically means what will be the highest concentration that I'm going to see. When is this thing going to get here? So I know there was a spill 20 miles upstream. When do I have to turn off my pump for my city's drinking water supply or for the water I'm using for irrigation? And finally, okay, we know this is true at one time of the year. What if it happened at another time of year where you might have a difference in flow rate, which would give you a difference in advective velocity, a difference in mixing, where you might have a strongly gaining instead of a weakly gaining stream that might affect transient storage. So these solute tracer studies are, for me, a diagnostic tool. They're teaching us all about transport along study reaches, how it varies in time, how it varies in space, and they're really empowering because they let us start to make predictions of events that haven't yet happened. And I find that useful because it starts to inform the way that we manage our water resources. All right, so having watched this video and done the associated reading, hopefully you've at least got some sense of what a solute tracer study is, why we might do them, what kind of useful things you can answer from them. What we'll dive into next will be some background on the data set that you all will analyze through the course of this module. And then we will get together and start talking about advection, dispersion, discharge, and starting to actually design our own solute tracer studies. So with that, I'll hang up. I'll let this video stop for now, and I will see you in the next one. Thanks, class. Have a great day.